All right, in this section, we're going to be talking about integration by substitution. And for the most part, you can do these problems more than one way, but sometimes you really can't. And they're more maybe a way that you see that might actually be easier than what I would do. So, the first problem that we're looking at here is number 4. And yes, we can fill all this out, but we want to try to go a different way. So the idea here is you're looking for something that when you use the u substitution, so we're going to set u equal to something, we want that derivative to be present in the problem, or at least a part of the derivative to be present in the problem. That makes things a lot easier. So here, if I look at the x squared plus 1, the derivative of that is the 2x, and I see that on the outside. Usually we have kind of like an inside and an outside of the problem, and when we have that, it makes our lives a lot easier. When we don't, sometimes we see some products here, but you need some part of the derivative of what you're letting u be to be present in the problem. So we let u be the x squared plus 1, and we take the derivative, or technically the differential here, we get the 2x dx, that's the dx part makes the differential versus the derivative. I see 2x dx in the problem. 2x dx is equal to du, so let's replace everything that we see. So this is u. You notice I didn't bring the squared on here. I just let it be. So it's u squared, and then all of this is my du. And now we have something that's a much easier thing to take the antiderivative of. Now a couple things to note. If there are bounds on this, like 1 to 2, you don't want to put 1 and 2 here. A lot of times I cheat and will leave the bounds off and then bring them back at the end when I resubstitute back in my x's. If I'm going to put bounds on here and do everything in terms of u's, I have to figure out what these x value are as u's. So if x is 1, u is 1 squared plus 1, or 2. If x is 2, u is 2 squared plus 1 is 4 plus 1 is 5. So that's what I should have on my bounds. So this antiderivative here is, well, u to the third over 3. Now, again, if it is an antiderivative with bounds, I can now plug in my new bounds, 5 and 2, or I can write this back in terms of x's. So u is x squared plus 1 to the third over 3. Now, since the problem didn't generally actually have bounds on it, when I do an antiderivative with no bounds, I have to put plus c at the end. So that's the main part. Now the tricky part is figuring out what you're going to set to be u, why you're going to use that, and what happens if it's not quite right. That's another tricky part. Alright, let's try another example here. So I see the inside of my square root. It would sure be nice if that was just an x, or just a u. And it happens to be that the derivative of the inside is sitting here on the outside. So u equals x cubed du will be our 3x squared dx. And lo and behold, there it is. So we have the integral of the square root of u du. Okay, well, what is the square root? That is u to the half du, and then I can use my power rule because now I have, there's powers. So this will be u to the 3 halves, add 1 to it, divide by a fraction or multiply by the reciprocal. And then resubstitute my u back in there. 2/3 u is the x cubed plus 1, and I personally leave it as 3 halves. But you could have it cubed and put a square root in there if you wanted to. And don't forget your plus c. So the hard part is picking out what's going to be your u. And what happens if it's not quite du? So that happens in 7 here. Alright, if you're wondering, for number 6, I'll just set it up for you. U equals, now if you did secant, like secant squared, you'd have to do all sorts of power rules. Don't forget, you have to bring down the 2, and then you have to do the derivative of the inside. Derivative of secant is secant tangent. So you can kind of sometimes when you get secant squareds and tangents do it more than one way. But that plus 3 really throws things out anyway. So I would have done tangent x plus 3. And the derivative of tangent, if you've forgotten, is secant squared. And these can be either order, so you can bring the secant and dx there. You can finish that one on your own. Alright, here's the next one. Now, the first one, that wouldn't have been too terrible. You FOIL all that out and distribute, you're good. I really don't want to FOIL this 4 times. Don't want to. So I'm going to let my u be what's on the inside. The x squared plus 1. The problem is, I have a 2x dx. And now here, all I have is an x dx. So there's a couple ways you can do this. One way, if it makes sense to you, would be, okay, I want a 2 there, so I'll put a 2 there. And to compensate for the 2, I'm going to put a half out front. And then there's your du. So if that makes sense, you're probably a little higher order thinker than most. I always had trouble when I was a student at doing that. It's taken me a while to really kind of wrap my head around it. So when I was a student, what I had to do is, anytime it wasn't quite right, I would solve for dx. And so dx is du divided by 2x. And now I'm going to replace my u and replace my dx. So let's see what we got. I'm not doing anything with the x right now. Not yet. X squared plus 1, that's u. To the 4th. dx is the du over 2x. Now the x's go away. This 2 that I was going to bring out front, remember the 2 and the 1/2? Now, there I've got my half. I can bring that out. U to the 4th du. Okay. You get the same thing either way. So this would be u to the 5th over 5, and then you get the 2, so 10 plus c, or x squared plus 1 to the 5th over 10 plus c. Now, every once in a while, I get a rare student that can almost do this in their head. Don't. Do your u substitution, be careful, because a lot of times you won't have 10, you'll have 5 down here. You won't catch the fact that you got to do something with that too. Alright, let's try a couple more. Alright, 8. It's a little bit more obvious that there's going to be a 2 involved here. So let's try this out. U equals 2x minus 1. Okay. Du is 2dx. Okay, well, problem is I don't see that x here. I need to cancel out that x, right? Now let's see what we got. X, we got square root of u. And then dx is just du over 2. I didn't cancel out the x like I did in the last problem. So the question is, well, what in the world do I do with that? Well, everything here is in terms of u's. I need to have just one variable. I can't have two. I can't just bring it out front or anything fun like that, like I can with a half here. So what we're going to do, if you don't get a variable to cancel out, is you're going to go back to the problem and solve it for x. So x is going to be u plus 1 over 2. Okay. Now, first glance, it doesn't seem to be very helpful. And I don't know, it might be helpful to do it like this. I'm not so sure. Let's just see what happens. I'm going to plug them in. U over 2 plus a half. And then we get the square root of u over 2 over here. What in the world do I do with that? Actually, looking at it, I think it probably would be better to do it right in this way. But since I went this way, let's stick with it. So at first glance, this doesn't seem very helpful. Let's write it as u to the half. Let's see if that works for us. Now what happens if I distribute? So u to the, well, 1 plus a half is 3 halves over 4 plus u to the half over 4. So why is this better than what we had before? Well, what we had before had the kind of nastiness inside the root, and that was a problem. I can't distribute my root across like both of these different parts. So I had to break this down to just u. And it kind of transferred the nastiness outside the root where we could deal with it easily. Alright, well, let's finish this up. So 3 halves becomes 5/2 over 4 multiplied by the reciprocal 2 over 5 plus u to the 3/2 and then 2/3 over 4, and in the end we have to plug in our original u's. So again, you could write these as square roots. I probably would go with the 2x minus 1 to the 5/2 divided by 10 plus 2x minus 1 to the 3/2 divided by 6. And we got it. Oh, don't forget your plus c. Alright, let's set up the last one and see if you can't knock it down. Alright, anytime you got a square root and it's got something inside of it, you're generally going to make the u be what's on the inside. You got a cosine and you've got something inside of it, you're generally going to let the u be whatever's inside of it. So u equals x cubed. Du equals 3x squared dx. Alright, well, good news is I got an x squared dx. The 3 is in the wrong spot. So you can solve this all the way for dx. Well, the other thing you can do is solve it for x squared dx. And just move the 3 over. And it really is up to you. If you see it this way, that's probably a little bit easier. Well, this 3 is out front. And then we get cosine of x cubed, so u. And then dx is du over 3. So we end up having 1/9 integral of cosine of u du. Alright, antiderivative of cosine is going to definitely be a sine of u. And if we were good, you're not going to write u, you're just going to write x cubed. Now the question is, antiderivatives of sines and cosines, you got to be a little bit careful about them. The derivative of a positive sign is a positive cosine, so we are good. That checks out. You can check any of these by taking the derivative. Now, the hard thing about u substitution is there's a lot of different types of problems, a lot of different looks to these problems. So it's always, homework's important, but it's very important in this section. Unless you practice, unless you see these, unless you see them where you have different constants you got to take care of, and you check your answers in the back of the book, you're not going to really know what you're doing. You might understand it, you might think, yeah, sure, I got this. This is one of those that you have to practice. It just will not work for you. You might be able to do these examples, but you won't be able to do them on your own. So, good luck and happy hunting.